Hello again, my dear students, and welcome to the second part of this chapter related to analog measurements. In the first part of this chapter, we were more concerned about voltage, current, and resistance measurement through exploring the main idea of the moving coil, which was the first principle to have an ammeter, and then how we can extend the scale of this ammeter using shunt resistance, leading to voltmeter process with a series resistance connection, and finally an example of an active measurement, which is the ohm meter. Now, still under the umbrella of the analog measurements, we are going to go with more instrumental measurements, which is the cathode ray oscilloscope, or the CR, or what we usually call oscilloscope. Again, as I mentioned in the beginning of this chapter in my previous videos, although these kind of instruments are somehow a very out of stock, old radical measurements, still understanding the know-how of operation is very useful in order to gain knowledge about different measurement instrumentations and different control methods. And this what we are going to, or what we are trying to explore in this chapter. So let me start with sharing screen, and let's go together with this process. And our task today is to explore more about what is inside this bulk instrument, which we call oscilloscope. Generally, we can classify oscilloscopes into analog or digital oscilloscopes. Maybe in this section, we are going to be more oriented to the one on the left-hand side, which is the analog oscilloscope. And as you can see, a major difference between analog and digital oscilloscopes is what we call ADCs, or the analog digital converters. And already I mentioned this in the beginning of our module, that this ADC will be the main core or the main theme of our module this year. And we are going to give a very special focus on the implementation of an ADC. So that's why we are going to postpone a bit the one on the right-hand side, and let's focus on the one on the left-hand side, considering the analog oscilloscope. And this link showing a virtual oscilloscope, we are going to use it during this lecture. Okay, so let's go first with the general principle of how oscilloscopes work. Maybe we can classify, or we can categorize the block diagram for an oscilloscope into four main building blocks. The first, the one on the extreme left, is the electron gun, which is the source of electron, where electrons are emitted. And by the end of the day, once these electrons hit this fluorescent coating screen on the extreme right, each collision between the electron and the fluorescent coat, this will end up with one bright pixel glowing. So generally, you can, the beam you see in the screen of an oscilloscope is simply as a result of a collision of these electron beam into the fluorescent screen. But simply, if we have an electron beam, and if we have an electron beam, or electron gun emitting beams, and this electron beam hits the fluorescent screen, simply what you're going to see in the screen is simply one dot in the center. So the question is how we control this beam so that we can see a moving signal, for example, sinusoidal or whatever it is. And the answer is through these two controlling plates. We have vertical controlling plates and we have horizontal controlling plates. And simply, of course, we are going to discuss this in details, but in a very simple manner, these vertical and horizontal are these plates which are responsible for controlling the beam, either from the right to the left. Here we are considering the horizontal ones, or from the top to the bottom, where we consider the vertical ones. So let's go to the implementation, or let's go to the stage-by-stage process. So first, as I mentioned, we have what we call the electron gun. The electron gun, here we have the gun, and simply the gun, if you go to the theory of the solid-state electronics, you can understand that you can fabricate, or you can have an electron gun whenever there is a device or there is a material that can emit electron by giving this material an energy greater than what we can call the work function of the material, so that the electron escape from the material and go to the outer side environment with a high speed, which, if you remember, we call it the affinity level, which is the most or the last state in the material. So simply, if you act to have a material with some sort of a high potential so that electrons in the valency bands can escape to the outside the material, then you can have what we can call electron gun. As you can see, this electron gun is surrounded by the cylinder, and this is a very tricky way how to focus a beam, because generally, if we have a material that can emit electrons, generally this is what we can call a spontaneous process. So electrons are going to be emitted everywhere in a very random manner, but we need these electrons to be in a very directive way. So how we do so? It's a very simple. Let me try to make it using the camera. I will try to explore. Sorry, I'm sorry. Okay, so let me try to focus it for you. So let's assume that's this. I will make this cylinder in this direction. So this is a cylinder, as you can see. And let's assume that this cylinder is negatively charged. We know that electrons are negatively charged. So if my electron gun, let's assume that this gun is simply the electron gun. If the electron gun is inserted here, so electrons are emitted here, as you can see, electrons are negatively charged. So if the surrounding here is negatively charged, electron will try to go in the largest distance, in the farthest distance with respect to this cylinder. And simply, this largest distance or this farthest distance is the center. So I'm just trying to make it here. So as you can see, if I put it here in the center, that means that electrons are equidistant from the surrounding of the cylinder. So using this red cylinder, we can control, or we can ensure that our beam is very coherent, is very directed, unidirected to the center of the cylinder. That's why we have a single directed dot, which represents that a huge amount of electrons come from the gun, go through this cylinder and hit the screen, typically as a center, which is the center of the beam. So that's why we have this central. That's why we have this central, or say this cylindrical shape. And let me go back to the screen here. Yeah. So I think I have to go. Yes. Okay. So this cylinder is the one in here in maybe dark green. You can see it. So this cylinder is negatively charged, and we use this cylinder in order, or this grid. As you can see here, this is negatively charged. Okay. So, but we need to make some sort of control to this beam. What we mean of control is, for example, we need to adjust the focus. We need to adjust the brightness. And simply, you can now understand that, for example, the focus is the localization, and the brightness is the number of electrons. So whenever the localization of the electrons are more toward a very exact certain point, that means that the point will be focused. However, if the electrons are hitting the screen in a wider circle, that means that the focus will decrease a bit. Brightness is simply related to the number of electrons. So if more electrons hit the screen at a time, that makes this spot more and more bright. So this is how you are going to manage this, and we use this applied electrical field in order to focus. As you can see here, we have a variable field. Of course, this is a positive field in order to attract electrons, which is again negatively charged. So here you can adjust the focus. The higher the electrical field, the higher the attraction force, the higher the velocity, and then the higher the focus of the beam, and again the brightness of the beam. So you can adjust these two factors using the brightness and the focus. And this is the electrical gun. Now we turn to have these two plates. As you can see, this is a vertical plate and this is a horizontal plate. As I mentioned, the horizontal plate is mainly to tune the dot, the spotlight from left to right, and the vertical is mainly to tune it from right to left. So what's happen if we connect, for example, a sinusoidal signal, some sort of a sinusoidal signal, this is a negative sine signal, we connect it to the vertical one, or the vertical plate. However, nothing is connected to the horizontal plate. What you are going to see on the screen of the oscilloscope, simply, what you are going to see is that you are going to see this line, simply this line, simply because now, due to this sinusoidal motion, you are moving from down to top, and so on. But there is nothing that makes the oscilloscope scan from left to right, because simply you insert nothing to the vertical oscilloscope. So what you are going to see is simply a horizontal line, a vertical line oscillating in the screen of the oscilloscope. Let's play with that. Let's go to see this live. Okay, so this is our oscilloscope. And now let me, I'm just trying to minimize the screen so that you can see everything. So I will turn on the power supply. Let me also close the camera so that you can maximize your screen. Okay, and here let me turn on also this is simply an oscilloscope, but what I'm going to do here, my dear students, that I'm going to stop the sweep. So I will turn off the sweep. Again, can you see now? It's just a vertical line. So I turn off the sweep. When I turn off the sweep, this yes. So when I turn off the sweep, that simply means that there is nothing to make the oscilloscope scan from the left to the right. Nothing happened. So simply the line will be either central to the middle or central to the left based on the default setting for the horizontal plate adjuster or a tuner between the two plates. So simply, if the horizontal plates are defaulted to the middle, you can see this line here in the middle, or it can be like this one here to the extreme left. Same with the same meaning. Sorry, same with the same meaning that it's simply a very vertical line without a movement. So in order to adjust our oscilloscope to plot, to trace this sinusoidal signal, we have to have another action connected to the horizontal plates so that this action makes the horizontal plates sweep from left to right, scan from left to right. This is happened by what we call the triggering signal. So the trigger or the triggering signal is simply a process of moving that point from the extreme left, which is this point, and now by increasing the voltage, the electron beam will going to be deflected up to reach the extreme right point. So this is the point. So now using this trigger, we can scan the horizontal line from the extreme left to the extreme right. But again, here, what we see on the screen of the oscilloscope is simply a horizontal line because there is nothing inserted on the vertical plate. What if we make both? So as you can see here, we insert this on the vertical plate and we insert this on the horizontal plate. So by the way, or by the time the sinusoidal is moving, there is a scanner that scans the screen from the extreme left point to the extreme right point. So that's why you can see here this graph, which is the sinusoidal graph. This is very, very important, my dear student, in order to understand that having this input signal without trigger will not lead to a graph. It will be simply a vertical line. And having the trigger without an input means nothing. It means that we have just a straight line here. And simply, if you open an oscilloscope with embedded trigger by default, and you didn't insert a signal, what you're going to see is simply this horizontal line, which indicates 0 voltage, nothing in the input. So in order to have a graph on the oscilloscope, you have to have both. Your input signal, which controlling the vertical plates, and in the same time, you should have the trigger that's responsible for tracing the signal from the extreme left point to the extreme right point. And I would like, if you permit me, my dear students, I would like to make it in also another way using my paper here so that you can also understand it in a better way. So this is simply what we did. So this is the screen of our oscilloscope. And here we have, this is the y-axis where we, for example, we have this sinusoidal signal. Okay. And on the x-axis, we have something like that. So I will plot it, my dear students, in some sort of a 90-degree shift way so that you can understand. So I will make it like this. So this is the triangular signal. So this is typically the triangular signal, but I'm just rotated it 90 degrees. So still, instead of having this signal like this, I'm sorry, you didn't see. So instead of having this signal like this, I'm just rotating in 90 degrees so that it looks like that. Okay, so let's make it point by point. So this is point number 0. And this is point number 0. So this is out. Exactly. And once we start to move, let's say point number 1. So this is point number 1, for example. And again, this is point number 1. And so on. So if you start to trace this, you will find something like that. As you can see. So moving here, this is responsible for moving the point from the extreme left to the extreme right. And this is responsible for tracing the y variation, So simply you plot the signal. And this is typically what we did in our case. So this is, as you can see, as easy as you saw in this slide. So this is how we manage to trace a signal. But realistically, it's not that easy. We have to make a lot of adjustments to reach such a good synchronization between what is in the vertical alignment, which is a signal, and what is in the horizontal alignment, which is the trigger. So let's see what we are going to do. First, you will tell me a very simple question. That's not only to make it at once. So it's a periodic signal. We have to make this triangular, or it's typically a sawtooth. We have to make this sawtooth signal in a periodic way. That means that we have to have this triggering signal in a periodic way so that you can plot a cycle, a second cycle, and third cycle. So that's why we have this continuous vision on the oscilloscope. It's a running sinusoidal. It's not only one screenshot. So we have to have such a signal. We have to have our sawtooth between quotation, the triggering signal. We have to have this triggering signal to be in a periodic way, which is, of course, no problem. We can make a sawtooth, generated sawtooth signal, and we can make it periodic. This is no problem of that. But herein, we have a very important feature, which we call the flyback time. Because simply, a hypothetical sawtooth signal will say that, okay, this point will drop to this, and we will start a new sawtooth. But this is hypothetical, because you know in your background that there is nothing called instantaneous change. Any variation from high voltage to low voltage will take time. Okay, where is the problem? Let's take a time. Where is the problem? The problem is, in this time, your electron beam will make a reverse process from returning back from the extreme right point to go to back its starting point on the extreme left, which is the reverse process. Now you move here, you move from left to right. Now it's time to return back from right to left. And if you as an observer see this return back period or return back trip, this will destroy the signal. You need to see a continuous sinusoidal signal moving. That's why we have to make this flyback period with as the guard band in between, as you see. So this stage should be in a very, very quick manner, as if your eye cannot observe such variation. This is a very important feature you have to manage while you are designing your oscilloscope. So here, the target is to minimize this time as much as possible so that your observer cannot recognize that you make this flyback period and you start a new photos. Simply, it's typically like the traditional, the very old style of making videos or making cinemas, where we have a series of drawings and we are rotating, or we are just moving these screenshots or these photos in a very quick way, so that it gives you the impression like there is a movement. Typically, it's not a movement. Typically, it's a flow of series images that express, each of them is a static image, but by the end of the day, it gives you the impression of a movement, simply because the rate of rotation is very high, so that your eye cannot capture. This is typically what we are doing here. We are just trying to minimize this period so that your eye will not be able to capture that we are turning a new cycle in our trigger and so on. So this is the first point. A second important point is related to the trigger synchronization. When we make this graph, if you remember the graph I plotted in my white paper and even what we did here, we make a very trivial assumption that in one cycle of my input, which is the sinusoidal, I have one cycle of the totus, which is the trigger signal. That's why it ends up that I plot here in the screen one cycle of the sinusoidal. But definitely the input is variable. So for example, I can measure a sinusoidal with frequency 1 kHz, and then you come and measure with another sinusoidal with 2 or 3 or 5 Ks or whatever. So this frequency is dynamic. So the question is how you can continuously trace the frequency of your input so that you can prepare a triggering signal that is convenient with respect to your input. This is what we are going to see in the next slide. So simply, here is the idea. I need to adjust the triggering so that in each starting of the trigger, I have a start of my signal, as you can see. So these 3 red points are typically adjusted with the beginning of the trigger and the beginning of my sinusoidal signal. So simply what I say is a complete sine, a complete sine, and a complete sine, and so on. So this is a triggering process. But if this triggering is not adjusted, you can see this happen. So for example, now the triggering frequency is not adjusted with respect to, is not a multiple with respect to the input sinusoidal. In the first time, the triggering hit the sinusoidal in the zero crossing point here. So the first signal plotted is the black one. Now, in the next cycle of the trigger, because the triggering signal is not synchronized, it hit in the negative peak of the sinusoidal. So you start to see the signal coming from the negative peak and raising up here, as you can see. Then, again, due to the missynchronization, the third triangle hits a zero crossing point, but going down, not going up. So now this blue signal is going down. So as you can see, it ends up with out of phase signals. We don't have this continuous sinusoidal signal. Each time you see the signal on the screen, you see the signal in a different phase and in a different manner. Because simply each time you hit the screen, you hit the screen, or you hit the triangular, hits the input, it hits the input in a different point. That's why we have this missynchronization. That's why we should have self-synchronization, because again, the input is variable, so you cannot fix the triggering frequency. Definitely, if you fix the triggering frequency, you will face the problem of missynchronization because sometimes your input will not be aligned with the fixed frequency of the trigger. The result is we have to have this circuit. What is this circuit? This circuit is a self-synchronization circuit that is inserted inside the oscilloscope. So this is your input, which by force is a variable. It can have any sort of a frequency within the range of the oscilloscope. And this is a vertical alignment. So simply you connect the output to the input to the vertical alignment as usual. And what you're going to do is that you are going to make some sort of a pulse generation with respect to a certain reference point of your input. So this is an example. So here, this is a sinusoidal input. And I put some sort of a threshold. So whenever the sinusoidal crosses the threshold from low to high, as an impulse is generated. So here I insert an impulse. Here I'm not going to insert an impulse because now it's from high to low. I'm only inserting the impulse if it's from low to high. So it's raising edge. Again, this is an impulse. Again, this is an impulse. Again, this is an impulse, and so on. Now, using this impulse generated, I now have the capability to adjust or to synchronize a certain point in the sinusoidal signal. So if I start to generate a sawtooth signal that starts with these impulses, then I will ensure that every time the sawtooth start to generate, like this point and this point, it will start to generate at the same phase of the input signal. So every time I'm going to see the sinusoidal from this point. May one of you ask me why here we ignore this impulses? So for example, here we use half the frequency. So this is the period here. So the period here is doubled, which means the frequency here is half the impulse. Again, it doesn't matter. You can make it every frequency. So you can make the sawtooth like this. Every frequency, you can make it double, you can make it triple, doesn't matter. The continuity feature will always observe it by your observer as far as you are hitting the sinusoidal in the same point. So it's typically like, I show you, so let me use, I will try to find the annotate. It's like that. I show you this cycle, and then I skip this, and then I show you the cycle. Yeah. So from an observer point of view, you will not recognize that there is a dropped cycle in between. You are going to see a continuous sinusoidal moving. Another one, if you act to make your sawtooth like that, sorry for this bad drawing. That's why I don't use annotation in a regular manner. So here you are going to show all cycles. So either to use a triggering frequency exactly equal to the input frequency, of course this is acceptable, or it can be multiple of the input frequency. Again, there is no problem, you can make it. So it's a matter of starting each cycle with the same point where you end the previous cycle, so that you ensure the synchronization of your signal and the continuity of your signal. And this is the added value of having triggering synchronized with the input signal. Now, I hope that this somehow illustrates you the function of the synchronization. Another important feature we have in our oscilloscope is what we call the AC-DC coupling, and this may be interfaced to us the concept of using capacitance, or a lot of capacitors in our oscilloscope. So let me return back to the oscilloscope. So this is our oscilloscope, And this is the sweep. Let me turn it on again so you can see here the oscilloscope. And this is an offset. You know, this is a DC offset. So now this is a DC offset signal. What I mean by DC offset, that's a summation between an AC signal and the DC signal. For example, I have 3 plus 5 sine omega t. So we have a 3 as a DC offset, and we have 5 sine omega t as an AC. Now, if you go to this bottom, you can see that we have here 3 bottoms. In the middle, this is just a calibration ground. So whenever you go to the ground bottom, you should see an exact 0 level, because simply you now connect it as if you are now connecting channel 1 to ground. If we go to the DC bottom, that means you are showing everything. You are showing the DC offset and you are showing the AC offset. That's why the signal is shifted upward, as you can see. If you go to this now, you found that your sinusoidal signal returned back to the 0 offset. So it seems like this bottom rejects the DC signal and only pass the AC signal. So how we do such a process, how we can reject DC and only couple the AC in our measurement. Let's see that. So this is simply happen by using what we call the coupling effect. As you can see here, we have 2 paths. Either to pass in a short circuit, which simply will lead to a full presentation. So as you can see, the figure in the top, the sinusoidal signal is DC shifted. So here in the screen, you see everything. You see the sinusoidal, which is the AC component, and you also see the shifted offset. That's why the signal is shifted upward. But when you go to the AC coupling, I mean, when your signal pass through what we call a coupling capacitor, the signal returns back to the ground state. I mean, there is 0 offset. There is no DC component. Why this happens? I think if you already remember our electronics lessons, you will remember this, or maybe you can solve already. You can answer the question, because simply, whenever we have a capacitor, this capacitor have an equivalent of, if you remember, my dear students, this capacitor have an equivalent of 1 over J omega C. So once this capacitor is operated in a DC manner, which means that the omega is 0, the equivalent impedance is infinity, which is typically equivalent to open circuit. That's why simply, whenever you have a signal that have an AC component and a DC component, and you need to get rid of the DC component, what you are going to simply do is you are going to put a capacitor. The capacitor will, or the DC signal will consider the capacitor as an open circuit. So simply, the DC signal will not pass. For the AC signal, it will pass through the capacitor. But if this C and omega combination is well considered, I mean, for example, let's give an example. I have a signal of 1 megahertz. I have a signal of 1 megahertz, and I have a capacitance, for example, in the range of microfarad. So simply the 1 megahertz, which is 10 to the power 6, and the capacitance is 10 to the power negative 6. This will lead an equivalent compensation. So simply the equivalent capacitance, the equivalent impedance is nearly 1. So this is very low equivalent impedance, one in equivalent. So it seems like we have an short circuit condition. Of course, ideally the short circuit condition happen when 1 over J omega C tends to 0. So the higher the frequency you are operating, the lower this value, which makes this value tends to the 0 condition, which is the short circuit condition. So that's why when you are operating at relatively high frequencies, I mean, for example, megahertz or tens of megahertz, you will have you can see no effect for these capacitance in the AC operation, because simply the term 1 over J omega C tends to 0. But what happens if we are working at a relatively low frequency? What will happen, my dear students, is something like that. So this is what happens. So this is a square wave, and we will discuss later on why we choose a square wave. The square wave looks like this in the DC mode. It looks relatively nice. We have a square wave with sharp edges. Everything is very nice. And it's DC shifted. That's why we have a DC offset, as you can see. Now, when you change the button from the DC coupling mode to the AC coupling mode, what you are going to expect simply that this blue square wave should shift downward to be around the zero. This is simply the function of the AC coupling. But surprisingly, you find that, yes, it's now around the zero, which is the pink line, but unfortunately, it's fully destroyed. The signal, the edges, is not as clear as you can see in the top image. This is simply because, my dear students, the frequency you are looking at is very low. So in this case, I'm not sure if the frequency is written or not, but in this case, the frequency you are adjusting is something like 100 hertz, less than 100 hertz, and so on. Once the frequency you are adjusting is very low, that's make the capacitive effect appears. You cannot now consider the capacitor as a short circuit in the AC because simply omega is small, with still capacitance in the microfarad range, for example. So it's 10 to the power negative 6 times 10 to the power 2. If we assume that this is 100 hertz circuit, 100 hertz square wave, this leads to 1 over 10 to the power negative 4, which is 10K equivalent impedance. And here you have a capacitive effect that's easily observed. And this also leads to what we can call a filtering effect. And maybe you can ask me the question, why you choose a square wave for this example? Simply to maximize the effect. Because as you know, the square wave includes sharp edges. So whenever you have a sharp edges with high frequency component, we know that using our mass for communication knowledge or using our Fourier transform knowledge, we know that sharp edges is an equivalent for high frequency component. So whenever we have a high frequency component and we have a capacitor that will behave a filtering effect as if it's a low pass filter, what we are going to see is something like that. So now what we say is simply that the capacitance effect starts to dominate and starts to kill these sharp edges. So this is very important to recognize while we are using a low frequency measurement in our oscilloscope. Maybe we are going to consider this graph a few slides later on. We are going to consider this graph. Okay. The capacitive effect is not only related to the process of coupling. We also have another types of capacitance in our oscilloscope. And what we are going to show to you in the next 3-4 slides actually is very, very, very interesting and very, very important as well. First, oscilloscopes are electronic measurements or electronic instruments, which mean that in the oscilloscopes, we have some sort of electronic components and electronic circuits. And based on our understanding, we know that for any electronic circuit, we have what's called the input impedance. I think if you turn back to the electronics basic module, when you teach, when you have information about operational amplifier, for example, and the ideal operational amplifier, and we consider that for an ideal operational amplifier, the input impedance is infinity, and also when we have together the MOSFET and the BGT as an operational amplifier, as an amplifying either stage or double stage, we usually act to calculate the input and the output resistance and so on. So basically, for any electronic device, we have a resistance, we have an impedance. Usually, these impedance are in a form of a resistance and a capacitor. The most common values, let me say so, is around 1 mega ohm resistance and about 20 to 16 picofarad as a capacitance. So, what is the impact of having this input impedance on our circuit? Let's see together what is the impact. I'm sorry. So here, let's do it. So now we have a resistance and a capacitance. First, we have to consider two impacts. Let's say, for example, we have a transistor circuit like this. So this is, for example, RD, and this is, for example, RS, and this is a V input or whatever. And I told you, please use your oscilloscope to measure the voltage on the emitter, for example. So what you're going to do is simply you're going to connect your oscilloscope here. So this is your oscilloscope. And now you are trying to plot the voltage in, you are trying to plot the voltage across the emitter resistance. This is the ground, of course, and this is the emitter point. So the voltage you are going to plot now is simply the emitter voltage. When you do this measurement, you assume that there is nothing here. This is an open circuit. This is an infinite impedance, which is not true because we know that here we have a resistance and the capacitance. Maybe for the capacitance, you can slightly ignore the effects in this experiment if your frequency is not of a frequency of interest for the capacitance. For example, I mean, here, this is 1 over j omega c. We are now considering c in the picofarad range. So picofarad, which means 10 to the power negative 12. So if you are working, for example, in the megahertz, so let's say that this is a 10 power 6, this will lead off with an equivalent of 10 to the power negative 6, which is still a very high impedance because 10 to the power negative 6 in the denominator, which means that 10 to the power 6 in the numerator, which is a very high impedance, so you can ignore it as an open circuit condition. However, if you go to the RF range, where your frequency, where your operating frequency starts to be in the gigahertz, for example, you cannot ignore this capacitance. So this is the first point. But either you are going to ignore the capacitance or not. In both cases, you cannot ignore the resistance. So instead of RE, you have now this RE, or sorry, instead of RS source, I'm sorry, source. Instead of RS, you still have a resistance here parallel to RS. And this is, if you remember, this is typically such as the effect of the loading resistance in the voltmeter, if you remember the previous lecture. What we are trying to do is that we are trying to push this resistance to be very high. So it's 1 megahertz. Sorry, 1 mega ohm, I'm sorry. So this is 1 mega ohm. So if this RS, for example, is 1K, you can simply ignore. So it's 1K to 1 mega, 3 orders of magnitude higher. So you can ignore. But if this resistance is in the mega ohm, if your RS resistance is the mega ohm, you cannot ignore. So this is the first effect, which is the loading effect. The second important effect is the filtering effect. Let's say, so this is the input, and your signal is going to be to pass through this circuit. So what you can do, so this is the input with some sort of a resistance. This is, for example, the input resistance of your source. Let's call it RS, for example, and this is VS, and this is what you have here. So here you have this combination. What is the effect of this combination? Let's see. Here, I will call this R, CRO, which is the internal resistance of the cathode ray oscilloscope, and I will call this Z, CRO, which is the input capacitance of the CRO. This is a parallel combination. So simply we have here R, CRO, parallel to C, CRO. This will lead to R, CRO times 1 over j omega c CRO over R CRO plus 1 over j omega CRO. Okay, now if we use this in the denominator, if we multiply this on the denominator, we will get R CRO over 1 plus J omega R C R O C C R O. Try to plot this against frequency. So this amplitude ratio against omega. For omega, for very low omega, for DC operation, you can say that omega is equals to 0. This will cancel this term, and we will have R CRO here. Once your omega starts to increase, you will find that the denominator will start to appear. If you reach an omega of hypothetically infinity, these terms will tend to 0 because 1 over infinity is equal to 0. So this is something like that. And again, if you just flash back your memory, having such a response with respect to omega, that's lead to what we call a low-pass filtering effect. So another important feature associated with the input impedance of an oscilloscope is the low filtering effect or low-pass filtering effect. Back to the presentation. So considering the input impedance of an oscilloscope will lead to two important phenomena that we should track. The first is the loading phenomenon, which again have two sides. The capacitive side, which is related to your operating frequency. If you are operating at relatively medium frequency in the megahertz, so you can ignore the picofarad capacitance. But if you go to the gigahertz range, you have to consider the resistive loading, which is again a relation between your resistance and the input impedance resistance. The input impedance resistance in the mega ohm range. So if your resistance is in a comparable range, you have to consider, otherwise you can ignore. And the second phenomena that we should trace is a low filtering effect. It's like you have a low pass filtering effect. And this is typically what we reach when we say that for any oscilloscope, we have what's called the bandwidth of the oscilloscope. So whenever you are working with a certain oscilloscope, you have first to check that your operating frequency is within the bandwidth of the oscilloscope. So, for example, if the bandwidth of the oscilloscope is 30 megahertz, then you have to work with the operating frequency less than this 30 megahertz, and so on. Otherwise, your signal will be attenuated and you will face a lot of distortion problems. So this is an important point. Another important point, my dear students, is related to the probes. I think all of you enter electronics lab and circuits lab, and most of you maybe, or all of you maybe already use the probes. The probes is simply the wires we are using in order to measure a signal. It consists of two terminals, one terminal to the voltage and the second terminal to the ground. Simply, when we are considering a DC operation, we can see in this way. So here, as you can see, we have three parts. The probe itself, which is a resistance and a capacitor. The cable you are using, which is some sort of a transmission line. I believe that you already have a knowledge about transmission line from your electromagnetism. So it's a transmission line. And the input impedance of the oscilloscope. Again, this is the equivalent, which we already considered in the previous slide. Let me first make it a bit easy. And let me first start to think it from the point of view that it's simply I'm measuring something DC. So once I'm measuring something DC, it's very easy. It's about just I'm going to cancel all these capacitors because simply in a DC, the capacitor is act as an open circuit, as we already illustrated. So as a final process, I can say that I have only two resistance like that. We have the probe resistance, which is relatively about 9 mega ohm resistance, and we have the input impedance of the oscilloscope, which is about 1 mega ohm resistance. So it's a very straightforward voltage divider process between the 1 mega ohm and the 9 mega ohm. And what we are seeking is simply to get a voltage divider. So your input will be equals 1 over 1 plus 9, which is 1 over 10. From one side, you can be surprised now. Oh, so I'm just getting 10% of my signal. This is very bad news. 90% of the signal is lost in the voltage divider. But the good news is it's an already known attenuation. Usually, the problem with attenuation is not the attenuation itself. The problem in the attenuation is you don't know the attenuation. So you don't have the capability to recompensate this attenuation. In this story, the good news that we know that our signal will be divided by 10. There is an attenuation factor with 1/10 with respect to our signal. So simply, in your oscilloscope, you can simply add an amplifier with a gain equals to 10. So if you add this amplifier, which is already in our oscilloscopes, if you add this amplifier, you will compensate the attenuation due to the probe and due to the internal impedance or the input impedance of the oscilloscope. And you will return back the signal to its original value. So this is the good point. But, and that's why in oscilloscopes, we have what we call 1x and 10x. So the 1x operation is simply related to, we are multiplying the signal. This signal is multiplied with 10 gain unit to return it back to its value. If you go to the 10x mode, that means that I will get this signal as it is. And in this case, I'm only showing 1/10 of the signal. And maybe one of the questions you can think about, why we have this 10K mode. Usually it makes more sense that I multiply the signal by 10 to restore the 1/10 attenuation factor. But why should I make it in this way? So the question is, why I should maintain this 10K, this 10x mode in my oscilloscope. So let's try to discuss it. So I will again close this. Okay, so simply as we mentioned, we have here the 9 mega, and we have here the 1 mega. And theoretically, Vn here is divided by 10. In your oscilloscope, you will find two modes, what we call a 1x and what we call the 10x. In the 1x, we use again 10. So this V/10 is again multiplied by 10 again. So what you are going to restore here is Vn again, which is the normal mode. Usually, when we work with this normal mode, we have this value. But the oscilloscope offers another mode, which is this mode. So herein, what you get is Vn/10. The question is, why should I provide to my user this Vn/10? Actually, the answer is very simple. If you are measuring a signal of a peak-to-peak value, for example, or even peak value of 20 volts, or let's say not 20, of 200 volts, and the maximum value you can measure as an oscilloscope is 20 volts. Then if you go to 10/x mode, you are going to use this your oscilloscope to measure the 200, because what you are going to measure is not the 200, is the 200/10, which is 20. So the 10x mode enables you to still measure voltages, which is slightly, or not slightly, which is much greater than your amplitude limitations, because simply you are going to use this voltage divider in order to attenuate the input voltage by a factor of 10. So what you are measuring here is simply 10% of the signal, not the whole signal. That's why we keep this as an added value for our oscilloscopes. Okay, that's great. But the question is, what if we have an AC signal? Because simply what you see here, this approximation, is based on that we ignore the capacitance here. These three capacitance are ignored. But realistically, we can measure an AC signal where we cannot ignore the where we cannot ignore the oscilloscope's value. What happens if we are measuring an AC signal? Simply, if you are measuring an AC signal, your circuit will be like that. So this is the input Vin. First we have the probe, which is 9 mega, and we have here a capacitance. So this is CP, and this is 9 mega. And then we have the cable. So this is C cable. And then we have the input impedance of the oscilloscope. So this is the RCRO, and in parallel. And in parallel, we have the CCRO, as you can see. So this is the capacity. Okay. So you can consider, let me try to make it a better. Yes. Okay. So I think better if I can. Yes. Okay. So you can consider that this is Z1, which is simply the probe. And here, as you can see, we have the cable and the input impedance of the oscilloscope are in parallel with this CRO. So this is Z2. So Z1, so simply, you have something like that. This is Z1, and this is Z2, and here, this is V out, and this is V. Z1 is the parallel combination of R probe, which is 9 mega, with C probe. We just made an example before, so its equivalent will be R probe over 1 plus J omega R probe C probe. And Z2 equals this RCRO parallel with, if you remember, my dear students, from your circuit class, that whenever we have two capacitors in parallel, their equivalent is the summation, as if they are series. So it's parallel of C cable plus C CRO. So their equivalent will be R CRO over 1 plus J omega R CRO, open brackets, C cable plus C CRO. This is simply what you are going to do. So you have now an equivalent between these two factors. Now, based on this graph, Z1, Z2, ground, V in and V out. V out is simply Z2 over Z1 plus Z2. So if you return back here, this is Z1 and this is Z2. If we go to our slides, okay, here you will see that this is the equivalent. This is Z1. This is Z1 plus Z2. But now our target is to maintain this 1/10 factor. We need to reject all capacitance effect so that it's still 1/10. And when you go to the gain unit of time, you compensate it to return back to Vn, as we did in the DC operation. So how we are going to do so? How we are going to make this combination tends to 1/10. Here we have what we call the tuner capacitor. This tuner capacitor is simply CCP. You find it here, which is the capacitance here. This is the capacitance of the probe. we make the capacitance of the probe variable so that you adjust it. Between quotation, you calibrate your oscilloscope based on the value that makes this equivalent tends to 1/10. Simply, how we can make it, let's see. So, let me write the equation. So we have here R CRO over 1 plus J omega R CRO C cable plus CRO over the same term. So this is R CRO over 1 plus J omega R J omega R CRO C cable plus CCRO plus RP, which is the probe, 1 plus J omega RP CP. This term, these are similar, are equal to this term. If this term is equal to this term, you can simply cancel this, and it ends up to RCRO over RCRO plus R probe, which is 1 over 1 plus 9, which is 1/10. So simply the condition you are seeking for is 1 plus J omega RCRO times C cable plus CCRO should be equals to 1 plus J omega CP RP. Cancel 1 with 1, J omega with J omega. So RC should be equal to RC. If you act to make this RC equals to RC, then you ensure that the capacitance effect is rejected from the equation, keeping the 1/10 condition to your oscilloscope. So simply what you are searching for is this condition. Maybe one can ask, okay, so why we have this CP variable? Everything is constant. We have 9 mega, 50 pico, 16 pico, 1 mega. So why we have CP is variable? Simply because this number in the blue is simply a typical number. But when you go with the same probe from one oscilloscope to another, this 1 mega, for example, can change. So, for example, in one oscilloscope, it's 1 mega, and in the other oscilloscope, it's 1.2 mega. So, if you have here C as a constant, when you go to the 1.2 mega ohm oscilloscope, there will be a mismatching condition, which will lead to an attenuation. But as far as you have this tuner capacitor, you will be able to move forward, up or down the capacitance to keep this condition sustainable under different conditions. That's why we call this as a calibration condition for the tuner capacitor. Okay, so by the end of the day, you can see here, this is a typical example of calibrating an oscilloscope. First, we start with insufficient capacitance. So as you can see, the triangle, sorry, the square wave is not with sharp edges, as you can see here. Then we make an overconsumption, compensation. So we put a capacitance value which is much greater than what we need. So as you can see, an overcharging spike starts to appear up to we reach the desired value, which simply the value that sustains the equation RC equal RC, or the input impedance oscilloscope matches the probe, or the probe RC, or the resistance capacitance of the probe. And in this case, you have the square showing as a sharp edges. Again, the question, why someone can ask you this in an interview, and maybe in the lab discussion exam or whatever, why we are using square wave in order to calibrate an oscilloscope? Simply because we are seeking for the high frequency components. If you have a sinusoidal wave, most likely we will not face these problems because you have only a single frequency component. And this single frequency might already pass even with the presence of a capacitance mismatching. But in order to check the capacitance matching of your oscilloscope and to check the calibration process of your oscilloscope, you have to go to a sharp edges signal, which is the best one you can use here is square wave, where you can test the capacitance matching of your oscilloscope. Okay, so in the next part, which will be a small part, we are going to consider a very interesting XY mode where we can see that instead of having a time-dependent signal, you can plot two signals against each other's X and Y mode. And we also consider what we can call the external trigger. So see you in the next part, which will be a relatively small part. Thank you very much.